Hey, AP Chemisters, this is Mrs. Vanderlei bringing you new Blankwalle 17.7. This is free energy and chemical reactions. Here we're going to be calculating the delta G of a reaction. And notice you have this little not ought sign up here, okay? And we saw that before in your delta H and your delta S, and that is your standard free energy change here, okay? So the delta G naught is the change in free energy that will occur if the reactants in their standard states are converted to the products in their standard states. Again, what's their standard state? Is it like solid, liquid, gas? If it's a gas, it's at 1 atm at room temperature or 25 degrees Celsius. And so the same thing can be done here with delta G. We saw that in the last section with delta S, it was also in their standard states as well. Delta G cannot be measured directly. That's why we had that equation where delta G equals delta H minus T delta S, if you remember that. Finally, the more negative the value for delta G, the further to the right the reaction will proceed. What does that mean? The more products you make in order to achieve equilibrium. All right, we'll talk more about equilibrium later on. So, just for right now, the more negatives, the more products you're going to make, okay? It says equilibrium is the lowest possible free energy position for a reaction. If you go back and look at the very beginning of this idea of delta G, you'll see that it looks like a big loop or big U, and it's spontaneous if you ever go down the hill, and it's zero if you're at the very, very bottom. All right, so calculating free energy change. Okay, this equation should look very familiar. Delta H minus T delta S. Okay, so let's see what problem number 10 brings and how this is a little bit different from the other problems. So in problem number 10, what is given to you? You have the reaction, 2 sulfur dioxide gas with oxygen gas makes 2 sulfur trioxides, carried out at 25 degrees and 1 atm. Notice that their gases is at 1 atm and it's at 25 degrees. Calculate the delta H, delta S, and delta G. Notice they all have those little zeros, little naught signs using the following data. So there's your substance, there's your delta H of formation. Notice that they left off the units, or actually I left off the units, kilojoules per mole, by the way. And then there's your delta S naught, your joules per Kelvin mole. So these are the numbers that you look up. So if I give you delta H values, if I give you delta S values, can you solve for the delta G's, all right? So what's the first thing we need to do? Find delta H. Well, can you do that? Go ahead and do that right now. Pause this and figure out delta H. Come back when you're done. Okay, welcome back. Hopefully you got delta H naught is a products minus reactants. So I look up these numbers in the back of the book, or actually they gave it to us. Now, why did I leave off? This is my sulfur trioxide, isn't it? This is my sulfur dioxide. Why did I leave off oxygen? Oh, that's right. For your element, it's 0, isn't it? So you do it all together, you get negative 198. So go ahead and solve for entropy, if you would. All right, hopefully you figured it out. If not, pause it and keep working. But assuming that you are done, what's delta S? It's the same thing, isn't it? It is products minus the reactants. I'll put it over here, maybe. And then, oh, notice I did have to include oxygen here, didn't I? All right, and it is moles, but notice I left out the moles because there's a lot of writing. And I got negative 187 joules Kelvin. Now, does that negative 187 make sense? Hopefully so. You're going from 3 moles of gas to 2 moles of gas. It's becoming less disordered. So now what's delta G? Well, delta G is delta H minus T delta S. Notice what I did. I had to convert this, this value of negative 187 right here. But notice it's joules. I had to convert it to kilojoules, didn't I? And so I convert it by dividing by 1,000, and then I could multiply by 298. Notice I cancel out the K's, and I get negative 141 kilojoules. Okay. Any questions? I hope that's pretty self-explanatory, okay? So it's like a 3-step problem here. So that's problem number 1. It's the one that we first learned about with delta G, the delta H minus T delta S, okay? Well, what's problem number 2? It's an adaptation of Hess's law. All right, so if I had this for delta H, remember what I did? It's like a puzzle. If this is my goal right here, diamond's going to graphite, now I have these delta G values. How can I go ahead and figure out delta G for the reaction of diamonds going to graphite? Well, once again, what did I do? I rearranged that second equation, right? And so what can I do? I can cancel out the problems that are the same on both sides. I have some oxygens that are the same on both sides. I have some carbon dioxides that are the same on both sides. So what am I left with? Diamonds going to graphite. And so I had to switch around the sign just like in delta H. So my delta G is -3 kilojoules. It is negative, it is spontaneous, but because it's not all that negative, I don't make a lot of products, okay? I'm not going to make a whole lot of graphite. Let's go on to the next page and see what that third way is. Method number 3 is just like the ones you've already seen for delta H and delta S. It is the summation of your products minus summation of your reactants. So looking at problem number 11, it says methanol is a high octane fuel used in performance racing engines. Calculate the G naught. That should be a superscript for the combustion reaction of methanol, given the following free energies of formation. So go ahead, and you are given the reactants and the products down below. So go ahead and write that balanced equation. So pause this and come up with the balanced equation. All right, what did you get? Did you get this? Okay, so you have 2 methanols and 3 oxygens making 4 waters and 2 carbon dioxides. Hopefully that's right. So go ahead and do your products minus reactants, and let's see how you did. Okay, let's see how you did. If you're not done, pause this, all right, and then come back when you are ready. So this is what I did. I have products minus reactants. So that's why I had a balanced equation. So I have 4 waters plus 2 carbon dioxides minus 2 methanols and 3 oxygens. Notice the delta G for oxygen is also 0. The only one that's not 0 is your delta S, right? So then what? I did all this math, and voila, there I get -1378. What does that big, big, big negative number tell me? I'm going to make a lot of products, aren't I? Okay, I'm going to make a lot of products. So that's what that magnitude really tells me. So in summary, all right, there are 3 ways to calculate delta G. Do you remember what they are? Well, what's the first one? It's the one that we first did. It's delta G equals delta H minus T delta S. Then we had Hess's law. And then we used reaction equals products minus reactants. I do want something to look at something. On that sheet that has all these delta H, delta S, and delta G's, make note of what temperature those are all at, and that's for a reason, okay? So think about that, and we'll come back and probably discuss it in a little bit. I'm done for chapter 17.7 for now. We will not go on to 17.8 or 9 until we get done with equilibrium. So that's it for now. Take care. Don't wait to be great. Bye-bye.